Hello, everyone. Thank you for coming to the ITC Colloquium. Today we'll be hearing from Sanjana Curtis. She is an NSF Astronomy and Astrophysics postdoctoral fellow in the Department of Astronomy at UC Berkeley, and she is about to start as faculty at Oregon State. And before Berkeley, she was a postdoctoral researcher at the University of Chicago and received her PhD from North Carolina State University. She's an expert in nuclear astrophysics and nucleosynthesis, as we will be hearing about today. And she does research with electromagnetic transients and multi-messenger astronomy. She is also well known for her science outreach and was recently a top winner of the National Academy's Eric and Wendy Schmidt Awards for Excellence in Science Communications. So everyone, please welcome Sanjana Curtis.
Wow, thank you so much. Thank you for the invitation to be here. I also didn't know you knew about that award. It's pretty recent. Hi, everybody. Thank you for joining me during a somewhat stressful week for many people. I'll try to make this very much worth your time. So I will be talking about the nucleosynthesis of heavy elements in compact object mergers. And by compact object mergers here, I mean neutron star mergers and neutron star black hole mergers. I'm told that questions are pretty much on the go, so please feel free to interrupt me anytime I say something that doesn't make sense to you. I work at the intersection of nuclear astrophysics and multi-messenger astrophysics. Nuclear astrophysics being exactly what it sounds like, putting nuclear reactions in astrophysical systems in order to better understand how the elements around us were created in the universe. And multi-messenger astrophysics, which has really taken off with gravitational wave detections in the last 10 years or so, is a field where the idea is to try to collect different types of signals from the same event. So, for example, gravitational waves, as well as neutrinos, as well as light, as well as abundances, if you can measure them, to put together a more complete picture of the event than would otherwise be possible with just one messenger. And the way I go about all of this is mostly through theory and computation. I run a variety of models at various scales to better understand nucleosynthesis and transients from core collapse supernovae as well as compact object mergers. Today I'll focus only on the compact object merger aspect of this. Nuclear reaction networks, radiative transfer, that's sort of my bread and butter. I also work with observers to try to interpret signals that they've detected and to suggest directions in which we might look for interesting signals. Okay, so I'm going to kick this off, very simple talk format, with a quick introduction to the origin of elements. What do we know about it? Where do heavy elements fit into the picture? What are the questions we're asking? And then I'll just show you two projects, one related to neutron star mergers and one related to black hole neutron star mergers and how they play a role in the synthesis of heavy elements. And then I'll just wrap up very quickly, and maybe if there's time, I'll tell you a little bit about what I hope to do in my research group at Oregon State. Okay, so the goal of nuclear astrophysics is very grand. It's to understand the nuclear history of our universe. One part of that puzzle is the composition of our solar system. And by that, I really mean the composition of the sun, since most of the mass in the solar system is in the sun. And so if we measure the abundance of different elements in the sun, you get a figure something like this. And so on the y-axis is the abundance, the amount of stuff, if that's how you want to think of it, and on the x-axis is the atomic number. And we go from having a lot of hydrogen and helium to slightly less amounts of various elements until you end up on this tail of heavy elements all the way over here. Various features appear, a peak of iron group elements appears, this odd even pattern appears. All this is related to stars and supernovae, but also to nuclear physics, to properties of isotopes themselves. So the thing that we know for sure at this point is that the formation of this pattern, the formation of all the elements around us, did not happen at the same time, through the same process, or at the same sites. This is not an obvious thing. There was an idea around for a little while that shortly after the Big Bang, all of the elements were created. And that was our starting point. But this appears to not be the case. In fact, we now have this picture, and this is very broad strokes, of the origin of elements. This is a periodic table you've probably seen many, many times in your life. But the nice thing about this one is that it's color-coded according to the site that we think produced the various elements. So you can see the hydrogen and helium and a teeny bit of lithium coming from Big Bang fusion, Big Bang nucleosynthesis. Moments after the Big Bang, these elements were created. Then stars and supernovae really started to play a role in creating the elements from carbon all the way to zinc. Different types of supernova contribute to various proportions of these elements. Maybe you can even make something like gallium and germanium in a supernova. And then comes the group of elements that I'm interested in and that today's talk will focus on. Basically, elements heavier than iron, heavier than zinc, that group of elements, which was mainly made through neutron capture processes. There's two ways that you can do this. You can do slow neutron captures, or you can do rapid neutron captures. The slow neutron captures happen in low-mass stars. So during the AGB phase, you can, a neutron comes along every once in a while, an isotope can capture it, and you can make a heavier element that way. The other way is rapid neutron capture. And the site of the rapid neutron capture process was a mystery for decades. We were not aware. We had conceptualized the process, but we didn't know where in astrophysics this actually happens. Where do you find the right conditions? And of course, ideas were there, maybe in supernova, maybe in core collapse supernova. When a neutron star is being born, there's a lot of neutrons. Maybe that's where you do rapid neutron capture. Or maybe when there's a merger of two neutron stars, or if a neutron star and a black hole, you can do rapid neutron capture there. And so that is a scenario in the case of neutron star mergers, which has been confirmed in recent years, is that you can make our process elements, heavy elements, when two neutron stars merge together. Okay. So let's talk about neutron star mergers. What exactly happens in a neutron star merger? You start out with neutron stars in a binary. They are spiraling towards each other. Their orbit is decaying because they're losing energy through radiation of gravitational waves. As the stars get very close to each other, they also start to spiral towards each other faster and faster. They start to rip each other apart. And so during the merger, you get these tidal dynamical ejecta, mostly in the plane of the merger, pulled off the surface of the neutron stars. You can also get other types of ejecta that are produced right as the two neutron stars merge. For example, you can squeeze material out from the interface where the neutron stars shear against each other. Once the neutron stars merge, depending upon their properties, you can have a variety of outcomes. So this post-merger phase can be very interesting and important as well for mass ejection from a merger. Maybe the neutron stars are so massive that you immediately form a black hole or a black hole with a disk around it. Maybe you end up in this very fascinating regime where you have a hypermassive neutron star. It's supported by differential rotation, which decays away over time. And so it's a neutron star that lives maybe for 100 milliseconds, 200 milliseconds, and then it collapses. And you end up once again with maybe a black hole with a disk around it. Maybe you end up with a stable neutron star. So as you can see, this is, of course, a schematic, and there's many versions of this. Post-merger is pretty messy. And in order to know the nucleosynthesis in a merger, this is a phase that we really do need to get a handle on. OK. So the important thing is that all through this process, all through this merger and the formation of these various objects, matter is being ejected. In that material, you can do rapid neutron capture, and you can make heavy elements. So a little bit more about rapid neutron capture and this idea of making heavy elements by capturing neutrons. When you want to make a new element, you really want one more proton in the nucleus of the atom. The way rapid neutron capture, or neutron capture in general, works is that, so this is just a schematic. On the x-axis, it's number of neutrons. On the y-axis is number of protons. Say you are this isotope, and you capture one neutron. You can move over here, probably slightly unstable. As you capture more and more neutrons, you make more and more highly unstable isotopes with their nuclei bloated, full of neutrons. In rapid neutron capture, you can do this all the way to the neutron drip line, where the nucleus cannot accommodate any more neutrons. And the way to move towards heavier elements is through beta decays. So you can do this fast or slow. You can capture a neutron in beta decay and capture another in beta decay. If you do this, you stay close to the stable set of isotopes. In the rapid neutron capture process, you do this in a flash. You go to the very edges of the nuclear chart, and then you have a bunch of decays bringing you back towards stability. What that produces is a pattern that looks like this. And so again, on the y-axis, you can think of it as abundance. On the x-axis is the atomic mass number of an isotope. There's many different colors. These are just different levels of S process subtraction. The way we get the R process pattern out of that solar pattern is by subtracting what we think is the S process contribution to that pattern. So we have the R process pattern here, and the different colors, which hopefully you can see, are highlighting the first peak of the R process, the second peak of the R process, this range of isotopes called the lanthanides, elements from lanthanum to lutetium. They're very interesting for kilonova purposes, for the electromagnetic counterpart purposes. And then you have right over here the the third peak in the actinides. So this is your R process pattern that we're trying to explain and understand. Okay. Every time neutron capture happens, you don't necessarily make this entire beautiful pattern. One key quantity that decides how much of these different heavy isotopes you might make is the YE, the electron fraction. Sounds confusing, but bear with me. The YE is a measure of the neutron richness of material. So if your YE is 0.5, you have equal numbers of neutrons and protons. If it's below 0.5, you're neutron rich. If it's above 0.5, you're proton rich. So you want low YEs. If you want to make all these elements, you want the electron fraction to be low. So people have done studies where they found that if your electron fraction is below 0.25, you tend to make a substantial mass fraction of these elements and elements out to the third peak. But if your electron fraction is above that value, and this is for typical conditions in merger ejecta, there's other things in play, but generally speaking, if your electron fraction is above 0.25, you will not make a substantial mass fraction of these lanthanide elements. Maybe you just make something up to the second peak, maybe even the first peak, depending on how high your YE goes. Okay, so the neutron richness of the ejecta, the YE, is an important quantity. That quantity is in turn controlled by neutrino matter interactions. So when neutrinos in your ejecta interact with matter, they can turn neutrons into protons and protons into neutrons and change that ratio, change that neutron richness. So anytime you're doing a nucleosynthesis calculation, you really want to have a handle on the YE, and you want to have a handle on what the neutrinos are doing in your simulation. Yes?
So the natural decay of neutrons to protons is too slow? 10 minutes is too slow for the mergers? Or?
So you mean like free neutrons?
Yeah, without the neutrino, it can go to proton and electron.
Yeah. So mergers are like 1 second time scale is what I'm talking about here.
You're making this in 1 second?
Yes, making the full pattern in 1 second.
Okay.
Yeah. Okay. Right, so now finally the reason I'm fixating on the lanthanides comes up. It turns out that because of their atomic structure, lanthanides have an opacity that favors the absorption of blue light. So depending on whether you make lanthanides or not make lanthanides in your ejecta, you can get different spectrum of your kilonova, and you can get a completely different color of your kilonova. Kilonova being this electromagnetic transient that is powered by the decay of the heavy isotopes produced in the merger. So here you can kind of see, say, if you had no lanthanides, you would peak in the optical wavelengths. But if you start making more and more mass fraction of lanthanides, your transients start shifting towards redder and redder wavelengths, because the lanthanides want to absorb this part of the spectrum. Okay, so now we can relate our neutron richness to the kilonova color, and we can say, if you have a low electron fraction and you make a lot of lanthanides, you're going to get a red kilonova. If you have a higher than 0.25 electron fraction, you don't make a lot of lanthanides, you'll get a bluer kilonova. Okay? So these are sort of the key ideas that I want you to keep in mind as we move forward. So that's all great, but what actually happens in a merger? What are the properties of the different ejecta components? What is the YE? How does that relate to the transient? This is something that we're still working on and trying to understand. And one big motivation to keep doing this work came in 2017 with the detection of the kilonova AT2017 GFO. So this was an electromagnetic signal found arising from a neutron star merger event. The neutron star merger event was identified by the gravitational wave signal. And then in that part of sky, in that galaxy, we saw a transient that decayed away over a timescale of 2 weeks. Okay. When this event happened in 2017, I still remember attending the press conference at North Carolina State, where I was at the time. And we were all very excited, but we were also not ready for like the avalanche of papers that hit the archive. At the same time, there were like 70 new papers, and I'm still catching up to those. Okay, so this is very, very exciting for the multi-messenger community, for the nuclear astrophysics community, for people who care about the R process. We know now that there's a neutron star merger, that neutron star mergers can do our process. But of course, there's a lot of questions that remain. For example, how do you know the detailed composition of the material that was ejected? How much material was ejected? Are neutron star mergers the only way to do this? Are they the only site of the R process? All of these things are still not answered. So the kilonova that we did see was very interesting in that it had a spectral evolution where there were both red and blue components. So for a long time, people were predicting a red kilonova, then they were predicting a blue kilonova, then they were predicting some other color. And then when the kilonova finally shows up, it has both components to it. And this is usually how it's interpreted. Some people have 3 components that they fit to explain the kilonova light curves. But I'll just work with 2 for now. And so if you have an early blue kilonova, which was seen, that came from material that was about 10 to the negative 2 solar masses. That's how massive it was. And it was moving fast. Yes, question? Oh, sorry. Sorry to put you on the spot. And then the red kilonova component, so this is emission in the redder bands that became very prominent at later times. That was also about 10 to the negative 2 solar masses, 5 times 10 to the negative 2 solar masses, and it was moving slowly. So these are sort of things that we were able to infer by applying simple models of an expanding ball of material to the light curves that we found. But how all this relates back to a merger itself, where did the red component come from? Was it the tidal dynamical ejecta? Was it winds from accretion disks? And very interestingly, where did this blue component come from? Because nobody who had run a simulation at that point had predicted a blue component with quite those properties, quite so massive and moving very fast. So since then, many ideas have come up, and one of those ideas I'm going to show you now. So I'm going to focus on this hypermassive neutron star remnant phase, the phase where the neutron star lives for a short amount of time, and then it collapses to form a black hole and a disk. And the question we're asking is, what produced the red and blue components of GW170817? The red component could be accretion disk winds, but the blue component doesn't have a strong explanation. And we were offering basically this phase of the merger as the site, as the production mechanism for that blue component. Which elements were created and in what quantity, and what can we deduce or expect from future kilonovae? These are the sort of questions we're interested in. But with respect to the blue kilonova specifically, here is a rendering of what our simulation looked like. Basically, this had to be done in several steps. So the idea is to say, if you have a magnetized wind driven from this remnant neutron star object that forms after a merger, that wind can be moving fast enough and have the right composition and the correct amount of mass to explain the blue component of AT2017 GFO. It can give you that blue kilonova. But most of the time, there are no magnetic fields in merger simulations. Capturing magnetic field amplification is very tricky, so on and so forth. So we took a remnant that had formed in a merger simulation, and we mapped it to a GRMHD simulation, imposing a magnetic field that is expected to develop, and sort of just observing the properties, recording the properties of the material that gets driven off the remnant as a result of this magnetic field. And so that's this funnel of material that you're sort of seeing. This is just a function of time, 3 different timestamps. But this remnant lived for 12 milliseconds, and it was ejecting mass in this sort of magnetized wind funnel at a pretty high mass ejection rate, something like 0.8 solar masses per second. And then it collapsed to form a black hole, and that's when our simulation ended. So we had a short-lived remnant, and we recorded basically all the properties of this ejected material. And importantly, we did track all the neutrino matter interactions using a sort of approximate scheme that's currently state-of-the-art in these GRMHD simulations. Yes?
How long-lived the merger remnant was in GW170817?
Yeah, that's a good question. I don't think we have a handle on that because, I mean, there's ways to try to get at it by thinking about the short gamma ray burst. You might say, oh, you know, if you believe that you need a black hole to make the short gamma ray burst, then whatever that delay time was in between the merger and the formation of the gamma ray burst. But in general, the remnant lifetimes tend to be very uncertain. They can go anywhere from milliseconds to seconds. Yeah. Yes?
Wonderful. So, or if you don't have I don't want to blast you. So, right, yeah, that's really interesting. So I wanted to know, like, can you make a spectrum or actually like positions of different elements out of it? Did you ray trace them extra just to see how do they like behave, especially when you have this wobbling jet and so on?
Yeah. So if I'm understanding correctly, you're asking about the composition of this material.
Yeah, exactly.
We did track that, so that you're anticipating basically, well, this is just a fun simulation to look at when you run a simulation, but the next thing I'll show you is the composition of that material. And we trace it with tracer particles and calculate it in post-processing, essentially. So there's particles in the simulation of certain mass that are continuously tracking the temperature and density and neutron richness and so on. And then based on that, you can calculate what its ultimate composition would be. Okay, so this is the total composition pattern. So this is the whole jet summed up compared to the solar pattern of our process elements. And you might notice that we actually don't match the solar pattern, and we don't produce a high lanthanide fraction, which is good. That's what we wanted. The reason for this is that the electron fraction in the outflow is high. And when you add up the nucleosynthesis yields from that high electron fraction, very rarely there's one tracer particle that will give you the third peak of elements, but most of them sort of drop off around here. So the lanthanide fraction is low, promising for a blue kilonova. A little bit more detailed answer to your question is that there is sort of a gradient in the composition. So this is just the total pattern, but in general, the closer you are to the pole, the lighter the elements produced are. And as you move away from it, it's the heavier elements. So the YE gradient, YE is high at the poles and lower as you move away from it, and corresponding to that, the lightest elements are in the polar region. Yes?
You say that this has to mean that the fraction has to apply.
Yes.
So the temperature that drives it must be much more than needed to break nuclei.
Oh, yes. So,
So
yeah, exactly.
I don't fully understand how
Yeah.
the temperature is not killing the heavy elements.
Yeah, so that's a great question. So actually exactly that happens. In the beginning, you dissociate everything. And then as the ejecta expand away and cool down again, then you start forming seed nuclei. Basically, you form mostly maybe around ion group, those sort of nuclei. And then there's a lot of leftover neutrons still. And those start capturing on to the seed nuclei. Yeah. So another key thing is the seed nucleus to neutron ratio. If you don't have a lot of free neutrons left at the end of this process, you're not going to make our process elements. Okay. And so I calculated, corresponding to this jet, basically, what the kilonova should look like. That was the goal, to make a blue kilonova. And in fact, that is exactly what we found. Now, I had to play a small trick, but hopefully you'll forgive me for that. This is the kilonova that we got directly out of the simulation, a remnant that lives only for 12 milliseconds. And it produces, despite its high mass ejection rate, it only produces 10 to the minus 4 minus 3 solar masses of material, an order of magnitude lower than what we want for that blue kilonova component. So we get the right colors. You get a lot of blue ejection, but at the end of this simulation, you don't have the right amount of total mass. And so the kilonova is kind of fainter and shorter time scale, almost like a blue transient of some variety. But knowing that this phase of a merger can produce magnetized winds and the properties of those magnetized winds, and knowing that the lifetime of the remnant is so uncertain, so based on which neutron stars you merge, their masses, which equation of state you use, the strength of the magnetic field, you can get a range of lifetimes. So knowing that, we kind of turned this around and said, okay, how long would this remnant need to survive to make the right amount of mass for the blue kilonova? And so from that, we basically got 240 milliseconds would be the amount of time the remnant from this neutron star merger event survived, and then you would get the right sort of blue kilonova signal, and that still works with the GRB delay and so on. Okay, so a possible way to make blue kilonovae, maybe we'll see a lot more of these in the future. Maybe they'll have all sorts of mass distributions and velocity distributions. And so it remains to be seen how all this bears out with a larger sample of objects. Now, in 5 more minutes, I would love to talk a little bit about black hole neutron star mergers. So this was work that I did back at Los Alamos National Lab. And again, the questions we are asking about the remnants of black hole neutron star mergers are very similar to the questions I just asked about neutron star mergers, except in this case, it's a little bit simpler. There's no hypermassive neutron star remnant. If you merge a neutron star in a black hole, either the black hole will eat the neutron star, or it will disrupt it, and the disrupted material will sit in the disk around it. And so sort of that black hole disk system is essentially what you end up with, and with varying disk masses depending upon the properties of the binary that merged. So we wanted to do a little bit of a study of this. Simulate black hole neutron star merger disks of different masses, record the properties of the outflow, and see if you can hope to make, what color of a kilonova can you hope to make from these events. And actually the sort of accepted answer is black hole neutron star mergers make red kilonovae. Except we found some wiggle room there. Okay, so these are our 4 disks, basically ranging from about 0.08 solar masses to about half a solar mass. So we covered whatever reasonable disk mass range is as a result of these types of mergers. And then we simulated them, really Jonah Miller at Los Alamos Lab simulated them with this code called nublight. And so once again, I'll emphasize, we want to have a good neutrino transport scheme, good neutrino interaction, matter interactions in your simulation if you're interested in nucleosynthesis. This is currently the only code in existence that implements a full Monte Carlo neutrino transport scheme and really just solves that Boltzmann transport equation fully. Very expensive, but Monte Carlo is parallelizable, so we were able to get away with it. Yeah, so what you'll see is this disk sideways and top down, and then as the simulation goes, again, it has a magnetic field imposed, neutrinos are getting transported, material starts getting driven off of that disk and escaping. So we want to know what are the properties of this material. The typical velocities are 0.1 c. So already in terms of like velocity, you can't really make the GW1708 17 kilonova if you believe that that material is moving fast based on the spectrum and so on. So this is slow-moving material, but maybe you can still get some interesting composition behavior and interesting kilonova behavior out of this. And actually, that is what we found. So this one's a little bit involved. This is angle off of the equator, basically, measuring like this. And on the y-axis is time, and the color is the y. So you can, if you want to think about the disk at 50, the material coming off of the disk at 50 milliseconds, what did that look like? Sort of trace this line, and you can see that most of that material had an electron fraction maybe below 0.25 or so. But then as time goes on, and neutrino matter interactions are playing with this material, you can see the electron fraction beginning to change. So now suddenly, okay, close to the equator in these disk winds, you still have a lot of neutron-rich material where you can make lanthanides. But as you move towards the polar region, suddenly you're beginning to get more and more towards that equal number of neutrons and protons, towards conditions that don't favor the R process. Any questions so far?
So does that mean that from the equator to the pole, you're going to get transition from blue to red?
Yeah, that's a great question. So the answer to that depends on a few different things. One issue is that, as you can see, this was run for 300 milliseconds. And so we really only have a handle on the early phase ejecta right now. As the disk evolves further, maybe for a second or so, this behavior can change. There's different mechanisms that unbind material, and some of them favor low YE material. So basically what I'm getting at is over time it could be that there's just so much more material ejected at low YE that it swamps out some of this signal. But if at high latitudes there's nothing obscuring the ejecta, these early time ejecta, then we could still get an interesting signal out of that. You could get a blue kilonova out of that. Yes?
Some missing pieces to this puzzle, and one is obviously how much mass is in the disk versus the outflow, and second, there is optical depth, of course. The disk is much denser, so you won't see the inner layers. You
Right.
just see down to some optical depth. So
Yeah.
when calculating the light curve, you have to take that into account.
Yeah,
Right.
yeah. And for now, when we focus on kind of just the unbound material for the light curve, then we maybe don't have to worry so much about the disk optical depth itself. So we're just looking at things that just from the Bernoulli parameter appear to be unbound.
So it's a wind.
So the wind, yes. Okay, so in that wind, clearly you can do a range of nucleosynthesis. And that's, this is again the 4 different disks that we had, the complete nucleosynthesis pattern added up over all that material that was ejected in our simulation and compared to the solar pattern. And once again, for the total amount of material, we don't get the full R process pattern here. Now, I'm telling you that we know that neutron star mergers do R process and these types of systems do R process, but I keep telling you that you don't get the full R process pattern, so you might see some sort of disconnect there. But the thing is, this is just one component, right? There's other tidal ejecta, there's this long-term disk outflow that I was talking about. So it is possible that once you add all of that up, you go right back up to that solar R process pattern. But this is still interesting for the transient purposes. If you eject material that has that's moving fast enough and that has like the right composition and it's not obscured by anything else, you can still get a blue signal out of this. So it's possible that in the future, when LIGO detects a black hole neutron star merger, we do see something red and something blue, and not just a completely red kilonova. So even those events should be followed up at all of these relevant wavelengths. Okay, and this is just a calculation of the mass fraction of lanthanides in these ejecta. But yes, when you add up this with the dynamical ejecta, you go right back to the solar lanthanide fraction. Yes?
Abundance pattern change as a function of black hole spin? Does it have, is it sensitive to black hole spin? Or?
That's a great question. So this was something I was hoping to explore. So in retrospect, I wish I had done a larger set of simulations. We were focused a bit on producing massive disks. And so to produce more massive disks, you have to look at systems where the masses of the black hole and the neutron star are close to each other, and preferably the black hole is spinning fast. So most of these are high spin black holes, and that's how we produce the disks that you see. But it would be very nice to do a study where we only vary the black hole mass, only vary the black hole spin, and not intentionally vary the disk mass itself. I think if you look at Rodrigo Fernandez's work, maybe they've done a little bit more of this. So they don't do like GRMHD with Monte Carlo transport, so they run longer simulations and they can do this. Okay. So yeah, that was most of the things that I wanted to tell you about. And of course, please ask questions, but just to wrap up, this question of neutron star mergers, black hole neutron star mergers, heavy elements are produced, but in what quantities, what kind of signal can we see so we can actually interpret and understand what happened in the event. Different phases of the mergers can do different things. For the one signal that we have seen, it does appear that the blue component of that signal can be explained by a hypermassive neutron star that's magnetized and pushing out this magnetized wind. Other people have offered a different explanation from disk winds, but it remains to be seen who has the correct mechanism. And then which elements were created in what quantity, you don't get the full R process pattern all the time from every component. You can have a variety of things happening depending upon the properties of your binary, and you have to be very careful about the neutrino physics that you're doing, because that can flip your outcome, actually. So when I did a sort of simple neutrino transport scheme in this same simulation that I showed you of the hypermassive remnant, the kilonova was red, red, red. But doing a more sophisticated treatment of the neutrinos changed that color. Okay, what to expect from future kilonovae? I would say if we see a black hole neutron star merger and we see both a blue and a red component, we'll know that that came from the disk. There is no other way to do this, to do a blue component from a black hole neutron star merger. So it will be validation of this idea that disk winds can change their neutron richness enough to no longer be making heavy elements, which would be really exciting to see. And then finally, I'll say it would be very nice to be able to do this in a very simplified framework and quickly, and some people are working on this. But it's really hard to predict the properties of the transient without doing this expensive GRMHD with neutrinos and all of this messy physics included. But we have to do it if we want to get a handle on what we're seeing. Otherwise, you're always going to have an order of magnitude uncertainty on anything that you infer out of your observed signal. So this is what I'm working on still. And I want to pause for questions. Otherwise, I'll tell you a little bit more about my plans in the future.
So obviously, Los Alamos, you mentioned that you work there, has the best code that is not available to the academic community. That's what Dan Kaysen was complaining to me about.
Yes.
And I was wondering, since there is a ban on nuclear explosions, right, on Earth, is astrophysics a good approach for calibrating these theoretical models that Los Alamos has?
Yeah, so sort of two parts to the answer. One is that this particular code, this GRMHD, so on, this is now open source. Anybody can run it. But the kilonova calculation that I plan to do corresponding to this, those opacities are not available publicly. Now, but they are quite different from what I've heard in some respects from, say, the Tanaka opacities and the Kaysen opacities. So it could be that based on whether we see some spectral signature or not at a certain phase of the kilonova, we can say something about which opacities are more closer to reality. Another thing that is interesting is at Los Alamos, they'll talk occasionally also about trying to infer things about heavy, unstable isotopes from astrophysical observations. And so the idea there is, I mean, I keep showing this pattern like it's some sort of ground truth, but there's a lot of assumptions built into calculating this pattern. And one of them is the mass models that we use. So the farther you go from stability, the less we know about those nuclei and the various rates and even like the nuclear masses. And so if you start exploring all the theoretical mass models, each of these lines becomes a band. And so there's parameter studies that they're doing where they're trying to see if some particular shape in the pattern, if it shows up or not. Based on that, can you say something about actually this theoretical mass model of nuclei is correct?
Thank
So I was looking at this distribution of angle versus y, and
For this one, or?
in the like colorful plot.
Sure.
Yes. And so one thing I was thinking about is you see this really strong function of angle, and like in an accretion disk or something, if you ask how thick it is, it's like h over r is
The
sound
scale
speed
height,
divided
yeah.
by omega times
Yeah.
r. And so can we map here basically like the entropy as a function of angle versus like a simple metric like that? So essentially, is this reflecting the fact that to be further from the equator, it just has to have more heat? And like, so how much of this
Yeah.
gradient is like that simplest
Right,
explanation versus like maybe material getting deviated or more complicated sort of
Yeah.
fluid dynamics?
So the answer to that, honestly, is that I'm not sure. And the reason is that we want to study all the different mass ejection mechanisms, and we haven't yet. So some of the material that ultimately becomes unbound is due to magnetic forces. Some of it is maybe just neutrinos puffing up some of the material off.
And it's empty because of the centrifugal barrier. So
Yeah.
that has nothing to do with temperature, it's just because it's empty along the pores. Right?
Yeah. So that material can just puff up and kind of thermally ejected,
Yeah.
viscously ejected.
So I guess I was only
yeah.
thinking of then about the thermal gradient and not
Right.
about the magnetic stress that can
Yeah.
some of those places.
Yeah, so there's a number of things going on. And so I think there is some correlation with, like if closer to the equatorial region, it's mostly viscously driven material that tends to be more neutron rich. And then as you expose material more and more to the neutrino radiation coming from the disk, that can change the YE as it gets ejected and escapes based also on the expansion timescale and things like that. So I would love to explain this in a better way, but right now we just haven't looked at it hard enough to find that one thing.
Awesome. Thanks.
Any additional questions? If not, maybe we can hear about future plans.
Yes, okay. Yeah, so I am interested generally in nucleosynthesis and transients, and I'm interested in pretty much anything that explodes or merges or does something interesting in terms of nuclear reactions. As long as it's far away. As long as it's far enough away and happens just in the right part of the sky to put all our telescopes on it. Yeah, so I also do core collapse supernova, but that's not reflected here. And what I've been trying to do is bring together very high physical fidelity models of these things with the actual light curves that we observe and with the abundance patterns that we see. And you'd think that that's something that is done, but it's actually not so easy to take a GRMHD model or whatever, exploding supernova, and say, and produce 100 models like that for light curves. So essentially what people end up doing is somebody does this calculation, somebody else kind of does maybe nucleosynthesis, maybe there's like, maybe 6 to 10 papers where there's a 3D core collapse supernova model and you also have nucleosynthesis from that. And by the time you get to the transients, it's even more disconnected from all this history of what the progenitor was, what elements were produced, and so on. So sort of, I want to reestablish all of these links and predict all the multi-messengers based on the same simulation, the relevant physics done in different phases of that particular system, mapping from one to the next. It's always messy to map, but it's actually worse to not do that at all. So sort of running the GRMHD simulation, doing the nucleosynthesis, and then piping all of that to actually give you a morphology for your ejecta, a composition gradient for your ejecta, and then to predict the 3D transient light curves. That would be very nice to be able to do. But then, of course, we don't always want to run a simulation that takes 1 year to complete. So using all of this information to go back to the simpler models, change them, tweak them in ways that are more in alignment with what we now understand about supernovae and supernova explosions. So back in the day, or maybe even now, and I've done it too, one way of getting a supernova explosion to happen is to just deposit a bunch of heat in a zone of your choice. But is that necessarily going to give you a light curve that makes sense? So this is the large sort of, this part of the puzzle is what my group is going to be working on. That is what my collaborators work on. And together we're trying to piece it all together and also talk to observers and actually throw our models up against observational data and see if it makes any sense. And so this is a very small group at Oregon State. We're embedded in a physics department. Jeff and Javi do nanograv related work, so they had all this fantastic stuff come out about the hum of gravitational waves in the universe, the background, last year. I don't know if you were in tune with that. Davide Lazzati works on short gamma ray bursts and transients, basically gamma ray transients. And then I will be joining them shortly, and I work on nucleosynthesis and transients, as you heard, and both on core collapse supernovae and compact object mergers. So together, the four of us have sort of put together this multi-messenger group at Oregon State. So yes, that's what's happening next. If you have students who are interested in this kind of work and want to collaborate or chat or whatever, just let me know. Thank you so much for your attention.
If anyone has any lingering questions, feel free to ask now. I'm also going to advertise that there are a few slots still available for dinner, so that's in the email if you want to sign up.
Okay, I have one more question. So
Yes.
say you have 100 kilonova light curves, and you fit them with a simple empirical model, and that says what your blue to red mass fraction is. What do you learn from that?
Yeah, so that's a good question. So what you, well, again, there's layers to this in that, can you trust that mass fraction if you're doing it with?
Yeah, so let's just, or maybe I should
let's
say like
say
the light
we get-
fraction.
Okay,
Like if this fraction of the emergent luminosity is in the blue versus in the
Right.
longer redder.
yeah. So then you sort of have a handle on the light versus heavy element synthesis, right? And so then you can say, actually this much our process material was
Yes.
made in the
Yes.
merger.
Okay.
Once you're able to say that, and if you have a handle on the merger rates, you can say, actually, mergers are enough to produce the universe's budget of heavy
Yes.
elements. This is not going to be the case, I think, personally. But you know, that's the kind of game you can play. Another thing you might do is, again, like from the red and blue, if you get a net lengthening fraction out, you can measure these things in metal pore stars, for example. So I think Alex G did a paper on this where there's like the lengthenite fraction distribution of metal pore stars. And then GW17017, the kilonova from 2017, is sort of a little bit on the lighter side of that. Sort of, so kind of saying, if neutron star mergers are making this mass fraction, this lengthenite fraction distribution, they should be able to fill out this distribution, right? And just be able to explain it. But maybe there's some end of that distribution that they can't get to. So that would be an interesting thing to know as well.
All right, I have one final question still, because you mentioned it. I'm curious your thoughts on, I guess, core collapse supernova as another possible source of our process.
So at least in the simulations that I've done, you almost always end up with conditions that give you a weak R process, maybe first peak material, but
What
not
type of supernova?
in a core collapse supernova.
Like what masses or?
For the full range of masses. So this is kind of an interesting thing where when you form that, if you're forming a neutron star and you have some neutron-rich material from close to the surface of that neutron star being ejected sort of later in a neutrino-driven way. So that question is like, is it neutron-rich or is it proton-rich? Is it a mixture of both? Usually there is some small amount of neutron-rich material in these simulations. It's not a lot, but core collapse supernovae also happen like that. So, but again, it's weak R process, not heavy R process, almost ever. But if you do like a magnetorotational supernova or something like that, or that could still work. Yeah, we don't know.
Do you find that like weak? Do you find that weak R process for like any kind of core collapse supernova, or just like the specialized ones, like the highly magnetized?
Okay, yeah, so this is pretty much for any core collapse supernova, with the caveat that the ones I'm talking about are 1D simulations, but people have seen this in, I believe, in multi-D as well, that you always eject some small amount of neutron-rich material. So typically what it looks like is, and this is very interesting, and it's a result of the neutrino luminosities and neutrino matter interactions, but basically there's, if you're just looking at the ejected material and like the mass coordinate or something, close to the surface of the neutron star, there's always like some very neutron-rich material coming off of there. Then there's a regime where actually you have proton-rich material. And that's interesting for various ion group elements and their synthesis, and then you go back to being neutron-rich. Slightly neutron-rich, not as neutron-rich, as close to the surface of a neutron star. Yeah.
All right, let's thank Sanjana one last time.
Thank you, everybody. Yeah, I have some. Yeah. Thank you so much.